So yeah. So in simple terms, it means okay, total you have a total spread, of course, right?
Mhm.
Vary.
Mhm.
But let's break it down, okay? And
Mhm.
break it down into different buckets. And
Mhm.
okay, so what are contributing? So I know it's constituents or right?
Mhm.
Then see, okay, what are its, the variance that you see is composed of different variances within, right? Okay. And we want to see what are these constituent parts that are, giving this variation. Okay. So this we are decompose. Okay? Composition जोड़ने decompose होने का छुट्टी होने होता है, right? So we're
Mhm.
decomposing. Okay, decompositioning, decomposing rather, decomposing the variance. Okay, so means we are breaking it into its constituent parts. Okay, so let's see. The core idea is the core idea, right? Let's go. Imagine you are testing three different fertilizers on plants.
Mhm.
After a month, the plants are all different heights, right? Three different fertilizers, and the plants turn out to be of different heights, right?
Mhm.
Okay, and decomposition variance asks, why aren't all these plants the same height? Okay,
Mhm.
so why are they different? Okay, it breaks the individual plant's height, YIJ, into three separate parts. Okay, so now, okay, so why is there variation? है यो तीनवटा जुन variance हामीले देख्यौँ, है? Okay, so the underlying idea is, why aren't all these plants the same height? So it breaks down the individual plant's height into three specific parts.
Mhm.
Let's see the overall average, which is called the grand mean. Okay, this is the baseline, right? So we take all three plants' height, right? And then we can compute the average, the mean, which is the grand mean, right? So if they were all the same height, okay, then they all should have been the mean,
Same.
grand mean,
Yeah.
right?
Yeah.
If every plant were exactly the same, they would all would be the average height. Let's call it mu,
Okay.
right? Okay, so that is our baseline. This is our baseline, right? Mu is our baseline. Okay,
Mhm.
now let's see the treatment effect. Okay,
Mhm.
the treatment effect, which is the between group variance.
Mhm.
Okay, so now this is the variation caused by the fertilizer. Right? So if the fertilizer actually caused the variance, I
Mhm.
okay, that will be given by the
Mhm.
variance between the groups. Right?
Uh-huh.
Okay. If fertilizer A is better than fertilizer B, the difference in their means contributes to the total variance. Right? Okay. So one of the constituent part is maybe due to this fertilizer that's causing this variance.
Mhm.
Right? Okay. It's the fertilizer, and we basically okay, this okay might have been caused by fertilizer. One, you would have right? Possibility. The difference in their means okay. Okay, so the question is, did the treatment actually make a difference? Right?
Mhm. Mhm.
If it did, then of course there is bound to be difference in height, okay, which is due to this, right? Due to
Mhm.
fertilizer एउटा अर्को चाहिँ के हुन सक्छ भन्दाखेरि, and there is another, the root of variance or the cause of variance, which is within group or random variance. That is called the residual error. Okay.
Mhm.
So even plants getting the exact same fertilizers,
Yeah.
fertilizer won't be
Mhm.
identical, of course,
Mhm.
right? Okay. Due to tiny differences in soil, sunlight, genetics, etc. Right? And that is noise or an unexplained error. So how much natural variation is there that we can't explain? Right? So this is another constituent part.
Yep. Yep. Yep.
So Okay, now you want to ascertain which one is it. Is it due to fertilizer or due to this residual error? Right? Due to this
Mhm.
noise. I don't know. Right? Okay, so that is what we're trying to right, find out, figure out. Right? Okay. So okay, yeah, so so what how are we going to do it? Okay. So the variation, okay, of course you can compute the variance, but
Mhm.
where is that variance coming from? Is it due to the treatment effect or the residual effect? That is what
Mhm.
we're trying to find out. Okay. So yeah, and here's the the standard one way. Is one way or two way ANOVA. So we'll deal with that. Okay. Let's say something called one way ANOVA. The decomposition looks like this. So the YIZ, the height, is a result of the grand mean
Mhm.
alpha I, which is
Mhm.
one due to variance um,
Treatment.
due to the
Yeah.
yes, and the variance due to the error, this residual error.
Okay. Okay.
So that should decide the individual plant's height.
Mhm.
So if you see, the individual plant's height is mu, the baseline mean,
Mhm.
by mean, right? This much, okay. This contribution
Mhm.
coming from the fertilizer, in this case,
Mhm.
or treatment, right? And this error, right? Okay, the variation
Mhm.
coming from the error. See, right? Okay. So now decomposition went there, right?
Mhm. Mhm.
Mu
Mhm.
plus this variance, mu plus variance, and variance has two constituent parts. Okay, and we have decomposed it.
Yep.
Okay, so now if we look at the individual data points, okay, this is what it is. Okay, so now our okay, so what is the grand mean? The starting point for everyone. If they were all equal, then what height would there be? Mu.
Yeah. Yeah.
And
Be-
these are the differences. Different. Okay, alpha I, the treatment effect, and the epsilon ij. This is the residual error. Okay, and yeah, so that is what that idea, your idea we talked about, that is called the decomposition of variance, and which is the cornerstone, or that is the base of ANOVA.
Mhm.
Right? ANOVA.
Mhm. Mhm.
So we'll see more, right? This okay. Why does it matter? Let's see. So Stetson used this to calculate. So okay, this idea that we talked about, right, is used to calculate something called f-statistic, right, which
Yep.
will come next. We'll talk about f-statistic. Let's say t-statistic one has thing. T-statistic is for two groups. When
Mhm.
it's more than two groups, t-statistic doesn't work. We need f-statistic.
Mhm. 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 Mhm.
How is f-statistic? What is the basis of f-statistic? And this decomposition of variance is the base, or
Mhm.
uh, uh, that is decomposition of, okay, इसको core idea क्या होता है f statistic. Yeah, we compute the f statistic. Okay, and the idea is the decomposition of variance.
Yes. Okay.
Okay, and for example, if the treatment bucket is much larger,
Mhm.
so okay, so putting into buckets, right? Okay, and if treatment bucket is much larger than the error bucket, means this is
AI is
bigger than
is
this, right? Then we conclude that treatment actually worked, right? And if the error bucket is huge and the treatment bucket is small, then any difference we see are likely due to chance. Okay, so now let's see. It's the awkward analogy. It's a good analogy. Think of cake's flavor, right? Okay, so okay, when you taste a cake, right, it has very nice flavor, right? Okay, so now the total flavor, okay, it may be coming from, means it might be a result of many factors, right? When we see, it could be decomposed into, say, it could be the flavor might be coming from the amount of flour, the sugar they've used, right? This is one. Okay, that is the base, right? You have base, right? And the flavor, the nice flavor that we're getting, okay, maybe coming from what kind of flavoring they have done, chocolate or vanilla. And also, and then it could be due to the differences in baking, right? Oven variables, right? Okay, so decomposition helps you figure out if the chocolate flavor is actually noticeable over the different random differences baking, right? Okay, so that means, yeah. So the flavor that you just tasted, okay, okay, it could be due to the base because flour and sugar, maybe all the cakes are, um, made with these, right? So if you don't have, if flavoring is not used and oven variables are equal, then they should all taste the same.
Mm-hmm.
Okay. And this is one part, which is this one, right? And the treatment effect, which is this one right here. Flavoring is the treatment effect, right? Chocolate,
Mm-hmm.
vanilla, right? Okay. This is the treatment effect. And these are random variables. Oven variables, maybe, I know, the oven, maybe it was a high mode or low mode or, I know. So, okay. And other, oven code and settings are with you, right?
Mm-hmm.
Play, right? Okay. So means the total flavor that you get is a combination of these three.
Mm-hmm.
And you're trying to figure out whether this, for example, flavoring,
Changing. Yes.
did it play a role in
Mm-hmm.
specific, the distinctive flavor?
Mm-hmm.
Or is it just because of this
Mm-hmm.
taste
Mm-hmm.
cakes, right? And you see the distinctive difference in the flavor,
Yep.
right? Maybe it's not due to this, it may be due to, random chance that, in a particular, the cake that you're testing really, that tastes really good, could be because of this. They might have set their stove, oven in the right settings. Different those actually. Okay.
Mm-hmm. Mm-hmm.
So deliberately now, yeah. So now, yeah. But if you see now, I think we have a good idea of decomposition of variance,
Yep. Yep.
and
Yep. Yep.
that is the basis for F-statistic, right?
Right.
F-statistic, okay. And ANOVA is actually uh, is based on, or that technique is based on computing the F-statistic. Okay. Okay. So, okay, let me show you F-statistic area. Yeah. Okay. So your idea, I see. See, now I think we can understand the F-statistic. Okay. So let's see. F-statistic.
So, would you mind sending these
Yeah.
notes as well?
Sure, sure.
Böyle neyse. Ya da arkaya mı takıldım?
Of course, I will. Thank you much. Let's see. I think here, yeah, okay, F-statistic. Okay, right? So let's see. Let's talk about F-statistic. Okay. So now the F-statistic is essentially a signal to noise ratio.
Mhm.
Okay, just like you saw, right? Is it due to this treatment, which is signal, or just due to random noise, which is,
Yeah.
right, due to noise? So we're trying to see this is basically signal to noise ratio.
Mhm.
Okay, if the signal and the noise, or if your signal to noise ratio is one, then
Mhm.
there's not much of signal there,
Yeah.
right?
Okay.
And if your signal to noise ratio is high, there's a very good strong signal also there.
Okay.
Okay, so let's see. So while a t-test looks at the difference between two groups, t-test,
Mhm.
statistic allows us to compare multiple groups at once.
Mhm.
Here's the idea, right? Okay. So t-test is only for two groups. It cannot handle more than two groups. T-test. When you have more than two groups, three or more, multiple groups, and you want to, excuse me, compare the difference between multiple groups at once, at the same
Mm-hmm.
time, not
Mm-hmm.
in a pairwise way, no? Okay. Then you need to see at least one of them is significantly different from the others.
Yeah.
It doesn't tell you which one.
Okay. Uh,
Tell you the F statistic will tell you at
mhm.
least one of them is significantly different from the others.
Okay.
Okay, at least one of them, but it doesn't tell you which one.
Okay.
Okay, at least one of them is significantly different. तीन बताता हूँ सही है? Okay.
Mm-hmm.
Okay, so let's see the breakdown of and how it works, why we use it, and how to interpret. It's a ratio. F
Mm-hmm.
test is a ratio. Okay,
Mm-hmm.
let's see. The core idea, the core logic is the signal versus noise. We want to
Uh,
get good signal. We want to suppress the noise. It's always desirable to get
uh,
a good signal, means high signal, low noise,
yes.
right? And so that the signal to noise ratio is high. The higher the signal to noise ratio, the better.
Yeah.
Okay. Okay. And how do you get that? You want to increase this, you want high signal and low noise, and the result is, signal divided by noise. Right? Okay.
Mm-hmm.
So ANOVA, okay, so basically here's ANOVA. Okay. So ANOVA, we're trying to determine if the spread in our data is caused by the different treatments we applied, or is it just random luck?
Uh-huh.
Okay. So ANOVA, actually, what is ANOVA? ANOVA is, it computes the F statistic. Okay. Right? So now, so here's the formula. Right? Okay. So what do? In the heading, you compute the variance between groups divided by variance within groups.
Mm-hmm.
So, variance between groups, okay,
Uh-huh.
numerator, right? So numerator makes that is the signal. This is the signal part, and this is the noise part.
Mm-hmm.
So you want this variance between groups to be high, them to be as different as, you know, more the difference, more the variance, of course, right? Right? So, between groups, right, you want more variance so that your signal is strong, and you want the within groups variance to be low. This should be as similar as possible, right, within the group.
Yeah.
Okay.
Yeah.
So let's see. Just the numerator. This measures how much the means of the different groups vary from each other. Okay, and okay, means of different groups vary from each other. And if the groups are very far apart, this number is large. If the
Mm-hmm.
groups are very far apart, means the differences are very far apart, then it's good. This number is
Uh-huh.
large, and that is good.
Yeah.
Right?
Yeah.
You'll get the larger this value, the more significant it's likely to be.
Mm-hmm.
Okay, the result significant difference. Okay,
Mm-hmm.
all right. Our next thing is denominator, which is this one, right? TQ, that noise, right? It measures the variance inside each group. That is how much the individuals differ from their own group's average.
Mm-hmm.
And if the individuals in each groups are all over the place,
Number is
this
ours.
number is large. And okay, this is not good because you're increasing the noise. Noise increase
Yes.
when your F statistic low, no,
Mm-hmm.
right?
True.
Right. So the desirable property is this. Right? If you want to get you know, if you want to get the significant result, right? So
Mm-hmm.
it's a formula like you want variance between groups to be high and the variance within groups low. Variance within groups common भनेको, right? They are not too far off from within a group, right? Within a group, they are almost the same, their values are very close to the mean.
Mm-hmm.
Okay? Within the group, the values are very close to the mean. They're not too far off from the mean.
Mm-hmm.
Okay, which is a good thing, right? Okay, so uh, okay, so let's map this to the example that we saw before. Hey, and this is the fertilizer cookies made. Hey, so let's say we're testing two fertilizers, fertilizer A, fertilizer B, and let's
Uh-huh.
fertilizer C as well, because
Mm-hmm.
F1, so we need to have more than two,
Yes.
right?
Yes,
So
sir.
quickly a triangle, right? So just to get a sense of it. So we have one, two, three, right? We have some plants, some plants, some plants, some plants, right? And this plant gets fertilizer A, treated with fertilizer A, fertilizer B, and fertilizer C, right? Okay, so now the variance between groups, okay? So variance between how much do they vary among themselves? A to B, B to C, C to A, and so on. Okay,
Mm-hmm.
okay, that is the variance between groups. And if they are high, that means they're significantly different.
Yep.
Right? And variance within groups is how do these data points within A vary, or how far off are they, you know, away from the mean?
Mm-hmm.
Say, इसका variance smaller, इसका पनि individually variance smaller, the इसका पनि variance within the group, right? Smaller means they're pretty much similar,
Mm-hmm.
right? Means the differences are coming from the industry due to
Yes.
soil, you know, the
Yep.
maybe
Yep.
the amount of sunlight they're getting, right? The difference within this is they're getting the same poultry fertilizer B.
Mm-hmm.
If you're seeing a lot of difference, even by using, you know, even if they are using the same fertilizer, means it's due to what? Due to maybe
Mm-hmm.
amount of water it's getting, maybe the sunlight it's getting, right? Other factors, which are noise. Right? The differences are coming from noise, that right to the noise, right? So if they are pretty much similar within itself, pretty much similar, that's a good thing. So that, you know, and you have a very high difference between, you know, inter between groups, high difference
Mm-hmm.
between groups, or very high variance means high difference, of course, right? And little difference within, and that is the ideal situation. That means you get high F. High F means statistically different. So at least one of them is, significantly different from others. Okay.
Yes.
Okay. Okay. So now let's interpret. Hey, interpret the value. So if you get F equal to 1, not good, right? Because the variation between groups is about the same as random variable within the groups, right? So okay, so this and this are equal, right? Variation between groups and variance within groups, they are equal. Only then you get F equal to 1 or
Yep.
close to 1,
Yep.
right? Theoretically, it's not a good result, right? This suggests that there's no real treatment effect. It's not statistically significant,
Mm-hmm.
right? Means that fertilizer, none of the fertilizers are not much different from each other.
Mm-hmm.
BC are almost same, right? Okay, we
Mm-hmm.
cannot reject the null hypothesis. We fail to reject the null,
Yes. Yes.
right? So what about F is greater than 1? Yeah, it's good.
Good. Yep.
Right? The more it is, the more the value of F greater than 1, the
Mm-hmm.
better it is, right?
Yep.
Okay, the variance in between groups is larger than the random noise. The
Uh-huh.
higher this number, the better. Let's say, for example, F equal to 15, the more
Yes.
likely it is that the difference we see are real.
Uh-huh.
It's actually due to fertilizer, right?
Yep.
Okay. At least one of them is significantly different, right? It doesn't tell you which one, but at least, right, it could be the difference between B and C. So this fertilizer may be very good, very, distinct from these two or whatever, right? Okay. And the more likely it's a different, and we see the real and not just due to chance. If you're greater, F is greater than 1, right?
Mm-hmm.
So yeah. So now, okay, so now we can go from f statistic to p-value, right? Okay, let's see. All right, so now, Eli, let's clear this out first. Okay? To know if an F score is good enough,
Mhm.
we look at the F distribution. Okay, we'll talk about this later. I'll show you the distribution, F distribution. Okay, we're going to look at the book matter. If the null hypothesis is true, meaning all groups are actually the same, the data is normally distributed, and the data is normally distributed. F type follows a specific curve. I'll show you that curve in a moment. Hey? Okay. And यसमा के हुन्छ, the x-axis में degrees of freedom हुन्छ, and on the y-axis, okay, there's the p-value. Okay, and we'll see. Right? We'll see. Now, okay, let's see. Why we use this instead of permutation test? Right? We can do permutation test. Right? Okay. So permutation tests are Softlink test, which we did last time. They don't care if your data is bell-shaped or not, or not. They just use brute force computation. Right? Yeah, it's
Mhm.
computationally very intensive, of course.
Mhm.
Oh, F test, it's just a mathematical shortcut. So you don't have to
Mhm.
do all that heavy, shuffling and then heavy computation में चाहिए ना, right? And you can assume that your data. So the assumption is that the data should be normal. And you don't need to reshuffle the data 110,000 times or whatever, hey? Okay, जुन कि यसमा गर्नुपर्छ त्यो चाहिँ अब यसमा गर्नु परेन. You don't have to, you know, shuffle the data, right? And then, compute the difference every time, right? You can just use the F formula and the distribution table to get an instant precise answer. Right? Okay, so एउटा तरिका यो भयो होइन. You can do this. This is one way to do it. Right? Another way is using the graph. Right? I'll show you that in a moment. Okay, so yeah, there are two. Right? Just a t-test. Okay, you can do a permutation test or t-test in case of two groups.
Mhm.
In case of multiple groups, more than two, you can do permutation test or the shortcut F test with much less overhead.
Mhm.
Right? Okay. Okay. Let's summarize here. Right? So what's the difference between t-test and F test? Right? T-test to F test. Groups compared. T-test exactly two, not more than two. It cannot do
Mhm.
more than two. F
Mhm.
test when you have two or more. Right? Two
Mhm.
right? So they're mostly more than two. Right? Usually three plus three.
Uh,
Right? Okay. What it measures? T-test measures the difference in means or sometimes median. Right? Okay. Which is the t statistic that you take, right? Okay, difference in means, and here it compares what ratio of different variances. Of course, it's comparing the ratio of variances
mhm.
within the right, within and between, right? Between and within. Okay, and the goal for t-test is to tell you whether these two groups are significantly different. Okay. And f-test को के होता is there any difference among these groups, any significant difference?
Mhm.
Right? Okay, it doesn't tell you which one, but okay, it will tell you at least one of them. Right? Okay, so I hope it is clear, right? Clear, Weissman. Okay. All right, so let's see, and yeah, let's our bookmark. I can show you how you can use the graph. Okay, so to compute or to yeah, to compute the this f statistic. Okay, okay, so let's quickly go there. Okay, so I got this one right here. Right, okay, so ANOVA. Okay, so okay, your degrees of freedom, I think it's n minus one. यति मात्रै याद गऱ्यो है. Degrees of freedom n minus one, right? Okay, and we're going to use that. Hey, why are we even looking at or you know uh, why do we need to even bother to know about degrees of freedom? Because that's what we're going to use to figure out the p-value from the graph in ANOVA,
mm,
right? Okay, so let's see, right? Yeah, yeah, and of course you can use this lm-pern, and then you can do AOVP, this
mm,
function, right? And then you can get all these, right? So यसमा चाहिँ iteration गरेर गर्छ है, permutation, है, permutation गर्दा it'll take this many iterations, and then it'll calculate the p-value.
mm,
Okay, this is the p-value. Okay, all right, and f-static we've already looked at, right? Okay, and f-static given somewhere. Okay, and f-static f-value, f-static equals f-value. This is f-value. Okay, and okay, degree of freedom. Right, yes, a degree of freedom 3. So okay,
mm,
so yeah. Okay, decomposition variance we have already talked about. Right, with two-way ANOVA. Okay, we'll see what that is in a moment. Okay, and this is okay, and I don't think त्यसमा छैन नि त्यो ग्राफ हुनुपर्ने हो. Okay, this chi-squared-मा क्या यसमा देखाएको छैन जस्तो छ. Okay, यसमा छैन रहेछ यो किताब. है chi-squared-मा चाहिँ त्यो छ है, chi-squared, we're going to use the chi-squared-मा ANOVA-को देखाएको रहेछ यसमा. Okay, no, anyway, so let's talk about this 2A ANOVA and then you. Okay, this company, there was 2A ANOVA. Okay, result. Yeah, yes, okay, yeah. So let's go further this way. Okay, so let's see of yeah, ANOVA मा जाउँ है त. So while the name mentions variance, the goal of the test is actually to compare the means of 3 or more groups to see if they are significantly different from each other. Okay?
mm,
Tool is variance, but the actual goal is to, compare the means
mm,
of 3 or more groups. But the
mm,
the tool it uses is the variance.
mm, mm,
So think of it as a super t-test.
mm,
T-test is limited to 2.
mm,
Test compares 2 groups. ANOVA can compare 3 more or 100 groups all at once.
mm,
Okay. The core idea is between and within.
mm, mm,
F-statistic, you have seen that, right? So ANOVA looks at 2 types of variance in your data to decide if the
mm,
groups are truly different. And you see,
mm,
it looks at 2 types of variation. One is between group, right?
mm,
Again, like F-statistic, and within
mm,
group. And that's the ratio between group variance divided by the within group variance.
mm,
And the within group is the noise, and between group is the treatment. Okay, and this is what we have seen before, right? You're seeing by Ali. And okay, what about types of ANOVA? ANOVA type, there are one-way ANOVA, two-way ANOVA, and MANOVA.
mm,
Let's see. Depending on how many categories you are testing, okay, you're going to use different versions of ANOVA.
mm,
Okay, so let's see. One-way ANOVA means there's one independent variable with 3 plus levels.
mm,
Right? You have only one independent variable. Okay, let's say, for example, does keto diet, keto versus paleo versus vegan.
mm,
Three diets, there's 3 groups: keto,
mm,
paleo, vegan.
mm,
And we're only one independent variable, this is type of diet.
mm,
Right? Okay. Does it affect weight loss?
okay.
This is the dependent variable. Right? This is the dependent. Okay. So now in this, when you have only one independent variable, right? So you're trying to see whether this is the independent variable type of diet, and you're trying to see the effect of type of diet on weight loss,
Yeah.
right? So you have only one independent variable. In this, you use one-way ANOVA,
Mm,
right?
yeah.
And if you have two independent variables, means,
Mm,
okay, the independent variables are the cause, okay? And the dependent variable is the effect, cause and effect with you. Right? A causal relationship. Right? So that means, okay, the cause is type of diet. And how does it affect weight loss? Okay, X
Uh,
and Y variables. Okay? X is, okay, so quickly, let's see, it's there. Say if you have X and Y variable, right? And here is independent in X, independent variable in X and dependent variable on Y. Okay, so for example, type of diet is the independent variable. So let's say we have three independent variables, and weight loss. Okay, so maybe this causes this much weight loss, this causes this much weight loss, and this causes this much weight loss. Right? The weight loss dependent is weight loss.
mhm,
Weight loss is being caused by the type of diet. Right? And this is the independent variable. And we have only one variable. When you have two, diet and exercise.
okay.
When you see ISMA, now that'll be like this. You see, three dimensional.
Okay.
Okay, diet, weight loss, and how does it affect the weight loss? Okay,
Mhm,
diet and exercise, diet and exercise, and how does it affect the weight loss? Okay,
mhm,
that's
mhm,
in that case you use two-way ANOVA, and MANOVA. MANOVA is multiple dependent variables.
mhm.
So, like, do diets affect? Now, you were, Yasma, we were testing for only, so one way, two-way, the dependent is only one.
Yes, sir.
Dependent variable only one. The MANOVA, your dependent variable is more than one.
Mm-hmm.
Okay. So, you're going to test the effect of, okay, diet on weight loss and cholesterol. These are the two dependent variables. Okay. So multiple dependent variables is MANOVA usage. Okay.
Mm-hmm.
So let's clear this. Now, okay, there's another term, something called omnibus rule.
Mm-hmm.
Right? Let's try to look at this way. Okay, let's see. And there's a nice video here, so I'm going to send it out to you. Please watch the video as well. Right? Okay, so okay, what is omnibus? Okay, one tricky thing about ANOVA that it is an omnibus test. This means that it tells you that there's a difference somewhere, but it doesn't tell you where. Right? So yeah, it will tell you that there's a significant difference between the groups, but between which groups? It doesn't tell you where's the difference. Okay, so result I will say ANOVA will can tell you, hey, these three fertilizers aren't the same, but what information is missing? It doesn't tell you if fertilizer A is better than B or if C is the only one that's different. Okay, so you see, this doesn't give you that information. So to find that kind of information, you have to run a post hoc test, like two kits SST. Okay, and once you get the significant ANOVA, right? So okay, if you get non-significant, you're done. Siddhi Ali, right? Non-significant. Right? If you get significant, and you need to know which one is actually better out of the those multiple groups, you need to use post hoc test. Okay? All right. Now, in order to use ANOVA, there are some assumptions.
Mm-hmm.
Okay. So for ANOVA results to be valid, your data usually needs to meet these rules. First,
Mm-hmm.
each group is made of different people and items. Okay. And each group is made of different people. And then normality, the data within each group should follow a bell shape, right?
Okay.
Normal distribution